Hello, everyone. Welcome to pre-lecture 8. This is going to be for our lecture on Thursday, February 2nd. So last class, we talked about what rate laws are and how we can use them to essentially figure out how fast a reaction goes, or at least the relationship between how quickly our products are consumed and what that means, or our reactants are consumed rather, and what that means for the rate and the order of a reaction. We're going to continue to build on that, but first I wanted to include a few slides just so you have them on how we determine the units for K. So we talked about this in class some. Oftentimes our units will be molar per second, but or the rate of a reaction will be molar per second, but the units for K will essentially vary depending on what our other terms in our rate law are. Okay, so if you think about a zero order rate law, in order to get the left side of our equation, so the rate being equal to molar per second, we would have to have the units of molar per second for K, because we would have no terms contributing to that. We have a first order reaction where, say, it would be equal to rate equals K times A to the first power, and A's units are molarity. Then we would have to have just basically molarity would come from that, and then the units on K would be per second, right? You can see second, third, and so on. And we did some examples of that in class, but I just wanted to provide this table from your textbook as well as an example, okay? All right, moving on, want to talk about what integrated rate laws are. And so thus far, we've discussed how we relate the rate of a reaction and the concentrations of those reactants. Another form each rate law can take is its integrated form. And so these are called integrated rate laws. And these can be used to determine the amount of a reactant or product that is present after some period of time, okay? And so that can be, of course, then very useful. And these rate laws are ultimately derived from calculus. That's where the integrated comes from. But instead of doing the actual calculus, we're just going to take the practical approach in Gen Chem that helps us understand the relationship between when a reaction starts and then how that relates to how we can determine then the concentration of any species at any time along the reaction proceeding. So if we think about first order rate laws, if we were to integrate this rate law here, where our rate is equal to K times A to the first power, we would end up with this equation, which is our first order integrated rate law. And so A sub T is just going to be the concentration of our chemical A at any time, and A sub naught is going to be the initial concentration there. We also have this term E, so that's our mathematical constant E to the negative K, and that's our same rate constant, and then T being time. Okay, if we were to graph this, we could also take the natural log of each side, and when we would do that, we would get a y equals mx plus b format for this equation, where y, our y-axis, will be the natural log of any chemical, in this case hydrogen peroxide in this graph, at any time. And then our y-intercept will be the natural log of the initial concentration. That would be right here. And then our slope will be negative K, and the variable x is time, right? So if we were to put this in a y equals mx plus b format, of course, here it says a y equals b minus mx, but you get the sort of idea there, okay? So that's what a first order integrated rate law would look like. If we think about what a second order integrated rate law would look like, if we were to integrate this term right here, we would end up with the expression where 1 over the concentration of our chemical at any time is equal to our rate constant K times that time plus 1 over our initial concentration. So as you might guess, if we were to graph that, we would end up with a straight line if this was a second order reaction, where 1 over our concentration would be our y-axis for the second order rate law, and our x-axis is going to be the time, okay? If we were to suppose this reaction was a first order integrated rate law and graph the natural log of that concentration of the C4H6 against time, we wouldn't get a straight line. And so that's one of the key ways we differentiate between different rate laws when we graph them, is we always want to look for what produces a straight line. And so in this case, when we do our integrated rate law for a first order integrated rate law, we end up with a curved line. So we know that's not going to be a first order reaction, but we do get a straight line for the second order fit. And so we know it's a second order rate law for that reaction, okay? Finally, we also have zero order rate laws. And so this is where if we were to just integrate this expression right here, where rate is equal to k, we end up with our zero order integrated rate law equation, which is the concentration at any time being equal to the negative rate constant times any time plus the initial concentration. So this is basically our linear relationship where our y-axis is just the concentration of whatever we have versus time. And assuming it is a first order reaction, we will end up with a straight line here. If it is, or not a first order, pardon me. If it is a zero order reaction, we end up with a straight line. If it is not a zero order reaction, though, we would end up again with a curved slope, okay? Right, so that is what that would look like for a zero order rate law. That'll be all we cover in the pre-lecture video. I hope that was helpful. If you do have any questions, of course, I'd be happy to answer them in class or via email. Please let me know, and I will see you in class soon.